All right, let's jump right into this explainer. Today, we're cracking a seriously fascinating biological code. We're talking about the hidden, microscopic, and quite literally life-saving mechanics that are keeping you alive at this exact second. You know, we rarely think about our blood chemistry until something goes horribly wrong. But beneath the surface, your organs are playing this endless high-stakes game just to keep your internal environment perfectly balanced. So grab your lab coats because we've got a clinical mystery to solve.
To set the stage here, we have to ask the ultimate biological question. What happens when your blood literally turns acidic? Think about that for a sec. We usually associate acid with things that dissolve metal or burn skin, right? So the idea of your own life force turning acidic sounds like something straight out of a sci-fi movie. But physiologically, it's a very real, incredibly dangerous threat.
To see exactly what we mean, let's look at a real-world scenario. We've got a 45-year-old guy sitting in the intensive care unit. 3 days ago, he suffered a severe myocardial infarction, a massive heart attack. And right now, his arterial blood gas report is just throwing off red flags left and right. His blood pH has dropped to 7.3. His bicarbonate, or HCO3-, is super low at 20 milliequivalents per liter. And his partial pressure of carbon dioxide, PCO2, is sitting at 32 millimeters of mercury. This patient is in serious trouble. And to figure out why, we need to understand the absolute baseline rules of human survival.
Which brings us to a magic number, 7.35. For us to survive and function normally, our arterial blood pH absolutely must stay within this agonizingly tight window, specifically between 7.35 and 7.45. Even a microscopic shift outside of this exact range, cellular function just starts breaking down. Our ICU patient is at 7.3. He's officially fallen off the tightrope.
It's pretty wild when you map out these danger zones. As you can see, the normal survival range is incredibly narrow. Drop below 7.35 and you plunge right into the red zone of acidosis. Spike above 7.45 and you enter the blue zone of alkalosis. With a pH of 7.3, our patient is sitting firmly in acidosis territory. He is slipping right out of the survival range, and his body is currently sounding literally every metabolic alarm bell it has.
So, what are the rules of the game here? Well, acidosis means your cellular pH has dropped below that 7.35 baseline. Alkalosis, on the flip side, is when that cellular pH elevates above 7.45. And just as a quick side note, the suffix emia, like acidemia or alkalemia, specifically refers to the state of the arterial blood itself. Our patient currently has acidemia, and it's being caused by severe acidosis.
So how do we actually diagnose this? These imbalances aren't just random chaos. They actually fall into very specific categories based on what's driving the breakdown. We divide them into metabolic and respiratory triggers. Respiratory issues are all about carbon dioxide levels, which, remember, your body treats as an acid. Metabolic issues, on the other hand, are driven by changes in bicarbonate, which acts as our body's primary base.
But before we look at how the body tries to rescue our guy in the ICU, we got to talk about the golden rule of biochemistry. Acid plus base equals neutrality. The absolutely crucial point here is that when an imbalance strikes, the body doesn't automatically cure the root cause. It just desperately tries to neutralize the blood to buy you some time. If you have way too much acid, your body is going to either try to hoard base or aggressively dump acid just to get back to neutral.
To achieve that neutrality, your body actually deploys a 3-tiered emergency response team. Think of it like escalating levels of security. First, the buffer system kicks in, instantly, within seconds. Next, the respiratory system fires up. That takes minutes to hours. And finally, the renal system, the kidneys, rolls in. They take days to fully engage, but man, they are the ultimate fixers.
First up, the immediate first responders, basically the paramedics of your bloodstream. These are chemical buffers that are already just floating around in your blood: bicarbonate, phosphate, and proteins. Within seconds of an acid-base imbalance, they bind to excess acid to neutralize it. But there's a huge catch here. They get used up incredibly fast. They're just temporary bandages, completely ineffective for long-term survival.
But you know, when those buffers inevitably start running low, the lungs step up to bat. This is respiratory compensation. Your central and peripheral chemoreceptors sense that the blood is getting way too acidic. And since carbon dioxide essentially functions as an acid in the body, the lungs get this panic signal: increase the respiratory rate. By breathing faster and deeper, your body literally blows off carbon dioxide, dropping the amount of carbonic acid in the blood to push that pH back toward normal. Okay, but what if the acid building up isn't carbon dioxide? What if it's a heavy, non-volatile acid like lactic or sulfuric acid? The lungs can't exactly breathe those out. That's when we call in the heavy lifters, the renal system. Like we said, the kidneys take a few days to reach peak performance, but they're uniquely capable of physically filtering out those dangerous non-volatile acids and flushing them entirely out of your system. The precision of the kidneys here is honestly just awe-inspiring. During an acidic crisis like our patient is dealing with, acidemia, the kidneys follow this strict, absolutely unyielding rule. For every single hydrogen ion or acid particle they actively excrete into your urine, they purposefully retain and reabsorb exactly one molecule of bicarbonate, the base. It is a perfect one-to-one biological exchange. Dump the acid, hoard the base. If we zoom in on a microscopic level, inside the renal tubular cells, it's like this brilliant little chemical factory. Water and carbon dioxide combine inside the cell, driven by a really crucial enzyme called carbonic anhydrase. This creates carbonic acid, which instantly splits. Then, the kidney literally pumps the acidic hydrogen ion out into the tubular lumen to be peed away, while simultaneously shoving the basic bicarbonate back into the bloodstream to raise the pH.
And get this, the kidneys even have a secondary trapdoor. If there's too much free-floating acid in the urine, it would literally destroy the urinary tract. So the kidney deploys ammonia, NH3. The ammonia acts like a molecular sponge, grabbing onto those secreted hydrogen ions to form ammonium, NH4+. This traps the acid so it can't leak back into the blood, letting it be safely flushed out with chloride.
Back to the ICU, the diagnosis.
All right, armed with everything we just learned about buffers, lungs, and kidneys, let's finally figure out what our patient's labs are screaming at us. Looking at the data, the formal diagnosis is metabolic acidosis. This is the most common acid-base disturbance, and it's defined by a primary deficit of bicarbonate. Normally, your body rocks a 20-to-1 ratio of bicarbonate-based to carbonic acid. In metabolic acidosis, that ratio completely collapses. Our patient's bicarbonate was sitting at an incredibly low 20. His base has just been utterly depleted.
So the real question is, why did his bicarbonate just vanish? Well, remember he just had a severe heart attack. A heart attack deprives your tissues of oxygen, and when tissues starve for oxygen, they produce lactic acid. This massive spike in lactic acidosis ate up all of his available bicarbonate buffers. Now, other triggers for this could be diabetic ketoacidosis, chronic renal failure, severe diarrhea, or even intoxication from things like ethanol. But for our guy, the trauma of the heart attack is what kicked off the avalanche.
And this condition doesn't just stay contained in the blood. It wreaks absolute systemic havoc across the entire body. Patients get severe headaches, lethargy, nausea, vomiting, and their skin even gets warm and flushed because of extreme vasodilation. If the medical team doesn't step in and help the body compensate, this quickly spirals into a coma and, ultimately, no way around it, death.
Now, remember our patient's unusually low carbon dioxide level of 32? There's a reason for that. As his metabolic system is failing, his respiratory center is stepping up as the hero. It's triggering these deep, incredibly rapid breaths, a classic clinical sign called Kussmaul breathing. He is instinctively hyperventilating to blow off as much acidic CO2 as possible, just desperately trying to artificially restore that 20-to-1 ratio we talked about.
Let's bring this all together. Imagine a seesaw. On a normal day, the heavy bicarbonate base and the lighter carbonic acid perfectly balance that seesaw right at 7.4. But in our patient, excess lactic acid crushed the bicarbonate side, tipping the whole seesaw into acidosis. So what happens? The lungs step in, blowing off CO2 to lighten the acid side, while the kidneys frantically try to manufacture more base to push the seesaw back to level. It is this brilliant, desperate physiological tug of war.
This delicate, kind of aggressive, and highly coordinated biological dance is happening inside you literally every single day. The human body's resilience is nothing short of an engineering marvel. As we wrap up this explainer, I want to leave you with one final thought. As you're sitting there right now, just breathing and existing, what incredible, silent work are your own organs doing to keep you perfectly balanced? Keep wondering, keep exploring, and we'll catch you in the next explainer.